How's it going, everyone? Hope you're doing well. All right. First off, does anyone have any questions on anything from the other course or this course? All right. Today we're going to look at a few sections from Chapter 2. Specifically, we'll look at sections 2.1, 2.2, and 2.4. So Chapter 2 is all about graphs and lines and inequalities. And these will be things that will be useful coming up in the other class when you get to linear programming for optimizing cost and things like that. These are kind of the basic skills that are necessary to do that stuff. And let's go ahead and start off with section 2.1, which is on graphs. Now we're talking about graphs. That means we have two planes, or two lines, that form a plane. We have what's called the x-axis and the y-axis. Each axis has a positive and a negative side. And if we were to label some points here, we have 1, 2, 3, and 4. And on the left-hand side, negative 1, negative 2, negative 3, and negative 4. So the x-axis has a positive side on the right, a negative side on the left. Y-axis, same situation, but vertical. Okay. So for the y-axis, the top side is positive and the bottom side is negative. So, which each of these two axes, it divides the space. Excuse me. It divides the space into 4 quadrants. 1, 2, 3, 4. Basically 4 different squares. Here's our positive quadrant where both axes are positive. So everything in here will be a positive number, basically. This is the one we work with most, especially when we deal with applications. Although if we're talking about profit functions, we might include the negative side of things. So It just depends on what we're looking at. But for practical purposes, most of the time we will be using where both variables are positive. Most applications end up in that area. So, except where negative values are possible, which, like I said, profit, we sometimes see negative values there. And there's a few other places where they crop up. So for a coordinate system, the way that we describe a point in the graph is how far it is horizontally from the starting point here in the middle and how far it is vertically. Okay, so this particular point is 2 points to the right and then 3 points up from there. And so when we describe that coordinate, we'll call it 2, 3. We always put the horizontal distance x first and then the vertical distance y second. Likewise, a point over here, this one would be -4 in the x direction and -1 in the y direction. So we can label that graph, or that point, -4, -1. Finally, if we do have a point that is right on either the x or the y axis, we move 3 points to the right. But since we're on the axis, we don't move up or down at all, so vertically we move by 0 units. So we'll say the coordinate there is 3, 0. So what would coordinate A equal? -1, 3. What about coordinate B? Right down here. Zero and -4. And let's pick one more. Coordinate C. -1 and -2. There we go. All right. Probably you're familiar enough with plotting points in a graph already. But it's nice to go over the basics there. We do label the quadrants with numbers 1, 2, 3, and 4. That's the other thing that we can do with quadrants. The first quadrant is always where everything's positive. And here, second quadrant, third, and fourth. We use Roman numerals to identify them. And we go counterclockwise, starting from that first quadrant. Quadrants we don't really need to worry about a whole lot. If we, like I said, most of the time when we're working with applications, we're going to stay in quadrant 1, except for the functions that could potentially have negative values, in which case we'll also use quadrant 4. As far as applications go, I don't think we ever use quadrants 3 or 2. 2 would imply that we have a negative input number, which I guess if we have a function that measures a certain, based on a certain year, if we want to go before that year, we put in a negative time value. But most of the time, those equations are only valid from a certain point, and we wouldn't go to the negative direction anyway. So, yeah, most of the time we'll stay focused on quadrant 1 and occasionally quadrant 4 for anything that could have a negative value. All right. So let's see if there's anything else I need there. Okay. We're going to look at the basics of graphing in this section, although we'll expand that further in section 2. And the general approach for graphing is, if we don't know how to graph something, then we make what's called a t-chart, where we pick some x values to plug in and then use those to find the y values that we can utilize to help us sketch the graph. For instance, if we want to sketch the equation y equals 2x minus 1. Now, what I would normally recommend is just pick some values for x kind of near 0. By staying close to 0, that means we'll keep our y values relatively small, although not always. And so by doing that, it keeps things a little bit simpler, basically. So if we want to plug in -2 for x, that means y would equal 2 times that -2 minus 1. So we take 2 times -2, which is minus 4, and then subtract 1. And so that gives us a y value of -5. So -5 would go right there. And that corresponds to our -2 that we plugged in. Now, if we have x equals -1, we could write it out like this, or since this is a relatively simple expression, we could also just plug it in mentally. Like 2 times -1 is -2. Minus 1 more makes -3. Okay. 2 times 0 is 0. Minus 1 makes -1. For x equals 1, 2 times 1 is 2. Minus 1 makes 1. And for x equals 2, 2 times 2 is 4. Minus 1 makes 3. Now, we have all these points now, so we can consider these like ordered pairs. -2, -5, -1, -3, 0, -1, 1, 1, and 2, 3. So we can go into our graph and plot each of these points. So we have -2, -5, -1, -3, 0, -1, 1, 1, and then 2, 3. Not a great straight line I've drawn here, but hopefully that makes sense. Okay. These 5 points actually all end up on a straight line. This is what we call a linear equation. A linear equation is one in which x and y are raised to the first power. So if we just have the variables raised to the first power, then the equation will be linear and therefore a straight line. So it's just x, it's just y. We don't have like x squared or square root of y or something like that that's different. Then we know it's going to be linear. And because it's a linear equation, we really don't need 5 coordinates to plot this function or this equation. We can just pick two points and go from there. So we could have just picked like 0 and 1, which are generally pretty easy to plug in, and use those 2 points to draw the rest of the line from there. Because we know from geometry that 2 points determines a line. Okay, but if we're not sure exactly what shape a graph is going to have, then it definitely helps to pick a few more points to kind of help illustrate where the curve is going to go. Okay. Now, let's look at another example. So let's try 2x plus 3y is equal to 6. Now, first thing that we notice is different about this equation is that we no longer have just y by itself. We have x and y on the same side of the equation equal to a number on the right hand side. And so in this case, it's actually beneficial to solve for y. So the question is, how would we go about getting the y variable by itself in this equation? Do you have any ideas? Bring the 2x over. And we do that by doing the opposite, so we'll subtract 2x. Now, I'm going to write this in a little bit different format. We'll talk about y later, a little bit later today. I'm actually going to put the minus 2x first and leave the positive 6 second. And then we'll divide by the 3. So that leaves y by itself. Now, negative 2 divided by 3 doesn't really give us anything. So we'll just leave it as negative 2 over 3. And then 6 divided by 3 does give us a 2 value. Okay. So we end up with this equation, y equals negative 2/3 x plus 2. And we want to pick a few values to plug in for x. Now we know we don't need to pick 5 like we did before, because this is a linear equation because x and y are to the first power. Because it's linear, we know we really only need 2 points. One thing we might do just to be safe is pick a third point, because if we plot all 3 points correctly, it should line up in a straight line, and if one of them's not on the line, then that tells us that we've made a mistake somewhere. So we can use that third point as a kind of a way of checking that the first 2 or all 3 of them are good, basically. The other problem we run into in this question is that we have whatever x is here is going to be divided by 3. We're multiplying by 2 over 3. That means we have negative 2 times x divided by 3. So we can actually, rather than just pick like -1, 0, and 1, I'm going to pick -3, 0, and 3. And the reason I would pick those numbers here is because we're going to have to divide the x by 3 in order to accomplish this calculation. So even better, we should pick an x that's a multiple of 3 to start with. That way we still work with whole numbers throughout the problem. Much better working with whole numbers than it is with fractions. So if we plug in x equals -3, we have -2/3 times -3 plus 2. Now, -2 times -3, that's 6, divided by 3 is 2, plus 2 again is 4. Okay. And again, as much as we need to write down these calculations, we can. It's not strictly necessary, like I said, especially if we're comfortable with the calculation. But I encourage you, if you're not quite sure, go ahead and write it out like we're doing here. X equals 0, -2/3 times 0, anything times 0 is 0, and then we'll add 2 to that. And then for x equals 3, -2 times 3 divided by 3. Since we're basically multiplying by 3 and dividing by 3, those cancel out. So it's a -2 times 1 plus 2 makes it 0. Okay, so that gives us a set of 3 coordinates again. Well, not again, but in this case. We got -3, 4, 0, 2, and 3, 0. You see that all of those points do line up on the same line, so that's why we picked a third point, is to kind of check to make sure the first 2 are correct. Really, we only need 2 points to draw a line, but the third is helpful in checking our work, basically. Alright, now these 2 coordinates right here are called intercepts. An intercept is a point where the graph crosses either the x-axis or the y-axis. Let me write that down. Okay, intercept, this is a point where the graph crosses either the x or the y-axis. Now, not necessarily crosses, it could just intersect, depending on the shape of the graph. If it's like something besides a line, there are going to be times it only intersects the axis but not cross, and that's something a little more specific for a different class. Anytime we deal with lines, they're going to cross the graph. So a point where the graph crosses or intersects either the x or y axis. Now, we specifically refer to them as the x-intercept and the y-intercept. If we want, we can separate them as specifically x-intercepts where it crosses the x-axis, or y-intercepts where it crosses the y-axis, or we collectively call them intercepts altogether. So there's different ways to kind of name those things. Okay. As far as how we would determine what those are from an equation, it's actually a fairly simple process. So for example, we'll use the equation 3x minus 4y equals 12. And the goal here is to find the intercepts in the graph. Okay. Now, if we think about it, here's a y-intercept. You can't quite see that. Sorry. And then here's an x-intercept. Now an x-intercept could be anywhere on this x-axis. But if we look at the coordinate for that x-intercept, what is always true about the y value? So any point that's right on the x-axis, what is true about the y variable, or the y value? 0, good. So for the x-intercept, we always have a value of y equals 0 because it's neither above nor below the axis. It's always right on the axis. Okay? So horizontally, we'll move x units, whichever direction that is. But we never move up or down, so y is always 0 at that location. By the same reasoning, for a y-intercept, x is always 0. Okay? Whether we go up or down to get to the y-intercept, we never move left or right because it's right on that axis. By definition, the y-intercept is right on the axis, and so the x value is always 0. It's never moved horizontally any direction from there. Okay, we can use that to our advantage. Anytime we want to find the x-intercept of an equation, we know we have to plug in y equals 0, and anytime we want to find the y-intercept, we know we can plug in x equals 0. So, if we say, okay, we want the x-intercept for this equation, we know we'll let y equal 0. If we let y equal 0, then that means we have 3x minus 4 times 0 equals 12. But now 4 times 0 is just 0, so realistically we just have 3x equal to 12. Which means x will just be 4 after we divide by 3. So that gives us an intercept of 4, 0 if we write it in coordinate form, because we have an x value of 4 and a y value of 0. Okay. By the same token, we can find y-intercept by letting x equal 0. Basically taking the same approach. Okay. So by letting x equal 0, we get 3 times 0 minus 4y equals 12. And again, 3 times 0 doesn't give us anything. So it's really just negative 4y equals 12 that we're working with. And then we can divide by negative 4. And so we get a value of, and that'll be a negative 3 once we divide. And our coordinate would become 0, negative 3, because we plugged in 0 for x, and we got negative 3 for y. Remember, we always put these in x, y form for an ordered pair. Now we can take those 2 points and mark them on the graph, and that'll help us sketch the graph of the equation. So we have 4, 0 and 0, negative 3. So 4, 0 is 4 to the right. 0, negative 3 is 3 down, and then we just draw our line connecting those 2 points. So this line is 3x minus 4y equals 12. So it turns out that by graphing the intercepts, we are able to use that to help us sketch the graph pretty quickly in some regard. In another sense, what we're actually doing, it's like we're making a t-chart and we're picking 0 for x and solving for y, and then we're picking 0 for y and solving for x. So if we plug in x equals 0, what will y equal in this equation? Yeah, we are working on graphing, so we do need to graph there. These are just examples I'm creating, but yeah, I did want us to graph them. Y would equal 6. Okay. Yeah, because if this is 0, we basically get rid of that term, and we're left with y equals 6. What happens if we plug in y equals 0? Instead? What would x be in this case? Negative 3, good. Yeah, if y is 0, we basically don't have a y value there. So it's like we have negative 2x equals 6. And we just divide by negative 2, so we get a negative 3. So that's another way that we could graph by finding the intercepts. Is we know the intercepts occur when either one variable or the other is 0. So we can set up a t-chart like that, where we have x equals 0 and find y, let y equals 0 find x, and this gives us a pair of ordered pairs. 0, 6, which is 6 up, and negative 3, 0, which is 3 to the left of the origin here. And again, just draw on our line, and that's the sketch of our graph. Now this won't always work perfectly, because sometimes we do end up with fractions here depending on what the numbers are. But we can still utilize this approach. There is another approach for graphing, though. Let's look at forms of linear equations. First off, we have what's called the general form, which is ax plus by equals c. A, b, and c could be any value, basically. And so These last two problems we're working with intercepts, we've been looking at the equations when they're in general form. Some number times x plus another number times y equals a third number. Okay. Now these may be negative or positive. We just start off with positive in the equation. And so we can see both of these, 3x minus 4y equals 12, negative 2x plus y equals 6, those both follow that general form. Next we have what's called the slope-intercept form. Y equals mx plus b. Now the slope-intercept form of the graph includes the slope and the intercept, oddly enough. We never would have guessed that from the name, I guess. Anyway, the slope is a measure of how quickly y changes as x changes. So basically, if we move 1 unit in the x direction to the right, for instance, how far up or down does it move vertically in that scenario? Like here, we moved 3 units to the right and then 6 units up to go from one point to the next. Okay, so from this point to this point, we go right 3, then up 6. Okay, and that's kind of a way that we can measure the slope. I'll talk about it more specifically in a moment. Same thing with this graph. To go from here to here, we go up 3 and then right 4. So that's what the slope measures, basically how steep of an incline a line actually has. So we can say it's the steepness of a line's incline. Or essentially how steep a line is. What angle it makes as it changes. Then we also have the intercept, which is our b value. Slope is m, and our intercept b. This is actually the y-intercept specifically. So there was a previous problem where we solved for y in order to help us set up a scenario where we can make a t-chart and graph the equation. That's basically the process of going from the general form to the slope-intercept form. Okay. So the slope, let's talk about this in more detail. The way we define slope is in terms of rise over run. Going from one point to the next, and generally we look at it from left to right. From this point to this point, how much has the graph risen vertically versus how much does it run horizontally? So when we talk about rise, it's a vertical measurement. And when we talk about run, it's a horizontal measurement. So rise over run. So to get from here to here, how far up do we go? And then how far over do we go? So to get from this point to this point, how far up and how far over we go? What is our rise and what is our run? Close, Luke. 3, 4 is the coordinate of this point. But this point is at 0, 1. So it's not a rise of 3. Actually, sorry, I put this backwards. It's 4, 3. That's my bad. So if this one's at 1 and this one's at 3, then vertically we have an increase of 2. And horizontally, if this is at 0 and this is at 4, then we go from 0 to 4. That means we've run 4 units to the right. So 1, 2 up, and then 1, 2, 3, 4 right. So our slope in this case, we would say, is 2 over 4, which reduces to 1/2. I will add that I didn't make a great mark for that point because it looks like it's kind of between the 2 points. Okay. But again, we look at the vertical change as compared to the horizontal change. Here we have the coordinate 1, 2, and here we have the coordinate 5, -1. How far down do we move to get from 2 to -1? 3 down, yes. Now, so we're going down 3. That's our rise. And our run, how far do we move to the right as we go from x equals 1 to x equals 5? What's our horizontal movement here? Four. Okay. Now, we saw the last one was up 2, but this one down 3. How do you think we would incorporate the fact that it's moving down into this slope? It's negative, right. So we'd say it's a negative 3. That means it's down 3. And then right 4 is our run, so over 4. And so that would be our slope in this case. Okay. So notice a line that has positive slope moves up as we go left to right, and a line that has negative slope moves down as we go left to right. Okay. So we would call this an increasing line or increasing function. This would be a decreasing line or decreasing function. Okay. And that's entirely based on the slope. Now, we don't necessarily need to look at the graph visually to be able to calculate the slope. It turns out we have a separate formula for that. Our slope formula, where m is our slope, is y2 minus y1 over x2 minus x1. This is the slope of the line that includes points x1 comma y1 is our first point, and x2 comma y2 is our second point. Okay. So we use the subscript to kind of denote which point it is that we're looking at. So we have the first point with the x1 and y1, and the second point with x2 and y2. And we always take the second one minus the first. For the y values, that tells us the vertical change, the rise. And then the difference in the x values shows us the horizontal change, the x, or the run. Okay, and then that's how we calculate rise over run. Now, like a point like this, 1 comma 2 and then 5 comma negative 1. So for instance here we would say this is our first point, this is our leftmost point, 1 comma 2, and this is our second point, this is the one that's on the right, so we'll go x2 y2. So it means x1 has a value of 1, y1 has a value of 2, x2 has a value of 5, and y2 has a value of negative 1. So if we apply our slope formula here, plug in y2 first, which is negative 1, minus y1, which is 2. On the bottom we take x2, which is 5, minus x1, which is 1. And then we just simplify that result. So negative 1 minus 2 is negative 3, and then 5 minus 1 is 4. Notice we get the same slope here as we did over here. So for what we've looked at so far, both in graphing equations, finding intercepts, and finding slope, we can do that from a visual approach, and we could also use an equation-based approach or formula-based approach. We notice that it works the same in both cases. It's just a question of what we're given versus what we have available as far as information. We're not always going to be given the graph of the line, but we may just be given a pair of coordinates, and we can use our slope equation from there. Or, if we're given a graph with 2 points marked on it, but we don't actually have any coordinates, we can just look at it visually and figure out the slope that way. Okay. So we go back to our slope-intercept equation, which we said was y equals mx plus b. Okay. As far as which one is y2 and x2, the x2 is always first and y2 is always, x is always first and y is always second. Whenever we have an ordered pair, it's always x comma y. So x is first and y is second. Now, as far as which one is 1 and which one is 2, normally go the leftmost one is 1 and the rightmost one is 2, but even if we switch them, we'll still end up with the same answer at the end. That's the part that might seem a little bit weird when we first start looking at this, is why is the slope the same when we switch the order of the points? Well, what's going to happen is the sign's going to change for both numbers from top and bottom, and that whatever signs we have will cancel out, basically. Okay. So the question then is, how can we graph an equation if we're told its intercept and its slope? Basically, if it's given in the form y equals mx plus b. Now again, when we're told that this is the intercept, again, this is the y-intercept specifically. So that's the point where it crosses the y-axis. So for example, we have y equals 2/3 x minus 1. So we know that we have a slope of 2/3 and a y-intercept of -1, or if we think of it as an ordered pair, 0, -1. Okay. Anytime we talk about the y-intercept, we know the x value is 0 and the y-intercept is whatever it is. Okay. Now, as far as what this tells us about this particular line, we have a coordinate that's on the line, and we have the slope of the line. So always graph the coordinate, the intercept, first. So 0, -1 is just right there. Okay. Now we have to figure out how to use the slope. Now our slope 2/3, again, this is rise over run, as we talked about. So from this point, if we rise by 2 and then have a run of 3 horizontally, that should get us to another point that's on the graph of this line. So our second step, after we've plotted the intercept, is second, we want to use the slope to get a second coordinate. Okay. So I said we rise 2 and we run 3. So we go 1, 2 up, and 1, 2, 3 to the right. So 1, 2 up, 1, 2, 3 to the right. And once we have this other coordinate, we can draw on our graph connecting those 2 points. Let's look at another example like that. Okay, this is y equals negative 4/3 times x plus 5. So the slope, in this case, is whatever's in front of x, which is negative 4/3. And our y-intercept is whatever constant follows x, which is our plus 5. Now we're going to slope. We know that's a rise of negative 4 and a run of 3. Now if we say that we rise by negative 4, which direction are we actually going? Up or down? Down. Yeah, anytime it's negative, we know it's going to go down and to the right. And anytime it's positive, we know it will go up and to the right. So whenever we draw our coordinates, the rise part, the top, is either up or down, but the bottom is always to the right. I think it's a nice way to be consistent about it, and that consistency should help us as we continue with this stuff. Okay. Now again, our y-intercept is plus 5, which means as a coordinate it would be 0, 5. Now we can think of it as either way. You know, we plug in 0, we get 5 for the y-intercept. That's what that means. But if we think of our y-intercept being positive 5, that means from the origin we can just go up 5 units, and that'll be the location of our intercept. Okay, whichever way we want to think about it, either way, this ends up being the same coordinate when we're done. Now our slope, we said had a rise of negative 4 and a run of 3. So we rise by negative 4, so 1, 2, 3, 4 down. And then a run of 3, so 3 to the right, 1, 2, 3. And again, just drawing the line that connects them. What is the coordinate of this point? Zero. Close. 3, 1. Yeah, notice we're a little bit above the axis still, so it's okay. It's okay. All right. Yeah. So we started at the y-intercept, which is plus 5, or 0, 5, if we want to make that a coordinate. And that's located here. And our slope was negative 4 over 3. So we rise by negative 4. It means we actually go down 4. So starting from our point, we go 1, 2, 3, 4 down, which puts us on 1. And then we have a run of 3, so we go 3 to the right, 1, 2, 3. And at this location, we'll go ahead and draw our coordinate. And then we just draw our line going through those 2 points. All right. Now, both of those examples, we had fractional slopes. But what if our slope is a whole number? Y equals 2x plus 1. So our slope is 2, and our y-intercept is plus 1, which we can think of as a coordinate 0, 1. But if our slope is 2, how are we going to get rise over run out of that? Can we express 2 as a fraction? What would 2 be as a fraction? We put it over 1, exactly. I mean, we could make it a little bit more elaborate if we wanted to. Like, we could say 4 divided by 2 is 2. But 2 over 1 is probably the most efficient way to proceed. Just whatever whole number we have, if we have a whole number slope like we do here, we just write it as being over 1 to create it as a fraction. Okay? So that means if our slope is 2, we think of that as 2 over 1, because then we need to rise by 2 and then go 1 to the right. So we start at a y-intercept of 1, and our slope is rise 2 and run 1. Okay, so go up 2 and then over 1. And again, we just sketch in our line connecting those points. Okay. Now, there are other lines that we need to talk about that they may be vertical or horizontal. Okay, so with vertical and horizontal lines, we do have equations for these, but it's not quite like the equations we looked at. You know, if we had y equals mx plus b, like we did, as long as m is not 0, this is a diagonal line. Sorry. There we go. So as long as m is not 0, as long as our slope is not 0, this is a diagonal line. Well, that certainly makes us think about, okay, what happens if slope is 0? What does it look like when slope is 0? Okay. In this case, if slope is 0, then y equals mx plus b becomes, well, if m is 0, then 0 times x is 0, and then 0 plus b is just b. So we just have y equals b in that case. Okay, y equals b is a line that is actually horizontal. Okay. And so if we look at that, you know, whatever the intercept b is, we'll have a line going through that location, a horizontal line. Okay. So basically the idea of horizontal line is y equals to a constant. And this is a line that has slope 0. Okay. And we contrast that with x equal to a constant. That's a vertical line. In this case, we say it has infinite slope, although in reality we just can't define what the slope is. But basically there's no measurement of the slope in that case, but we could also call it infinite. So that's y equals b. So to contrast that, we could say x equals a, finds a point A on the x-axis, and then we draw a vertical line through there. we think about slope as being rise over run, but if all our line does is rise, it never runs, then we can't really define its slope in that case. It's basically it's divided by 0, if you think about the run being 0 in this scenario. That's why we call it infinite slope. It just keeps going up. It never runs to the left or to the right. Okay. So with that in mind, what is the equation of this graph? Now, whether it's vertical or horizontal tells us which variable we're going to get. In this case, because it's vertical, it means we're working with the x variable. So going back what we talked about on the previous page, so if we have a horizontal line through a point, then y equals that point is the equation. If we have a vertical line through a point, then x equals that point is the equation. So really it's just a question of whether we have a vertical line or a horizontal line, whether it's x or y respectively. So looking at that again, what is our equation for this line? X equals -2. The way I like to remember that is that it crosses the x-axis at -2, never crosses the y-axis. So it's just x equals -2. Now the reason that we call that x equals -2 is that every single point on this line, let's look at the coordinates here. So if we look at all the points that make up this line, every single x value is -2, and it's really only the y value that's changing. It's increasing or decreasing, whichever way we're going. So to summarize this line, we say, well, it's every point, every coordinate where the x value is -2. That's everything that's on this line. And that's why we call it x equals -2. Okay. But more than that, I think it's easier just to remember if it goes through -2 on the x-axis, that tells us, whichever axis it crosses tells us which variable we should use. That's probably a better way of saying that. So what is our equation here? Drew it a little bit under where I meant to, but take it as a whole number value, please. Y equals 3. Yeah, because It's actually a little bit lower. That's my mistake, but it crosses 3 on the y-axis, so we'll say it's y equals 3. And so if I asked you to graph x equals 4, would we go to 4 on the x-axis or 4 on the y-axis? X? Mm-hmm. And would we draw our graph vertically or horizontally? Vertical. Okay. In that case, when they tell us or ask us to graph a specific function that has just one variable, we know it's vertical or horizontal. We do have to remember which one it is. So x is vertical, y is horizontal. Now that seems like a weird statement, because if you look at our x-axis, the x-axis is horizontal and the y-axis is vertical. But if we say we want to graph x equals 4, it means x is only one number, but y can be any different number besides that. Okay? X stays 4, but y can have any value in either direction from that point. There's different ways to think about it. Hopefully one of those resonates with you, and you have a good understanding of what's happening here. Any questions? It's worth mentioning that we started in section 2.1, but we're currently in 2.2 with when we've been talking about slopes and the vertical and horizontal lines and things like that. I want us to look at some of the problems that are on page 85. Again, section 2.2. So the first problems, we want to find the slope of the line that contains these 2 points for each of these problems. Okay. Then they want us to, given the intercept and the slope, they want us to find the equation of the line. And finally, find the slope and the intercept of the line that's in this general form to start off, which we kind of did already. I wanted to go ahead and look at those. I'll just, again, pick even problems, and we'll go from there. Uh, 85. Now, these three sections of problem we've already talked about how to do this. We've already done this to an extent, although maybe not specifically how they've asked us here. But the way that we proceed with a problem like this is we'll go ahead and label this as x1 and y1, x2 and y2. The reason is I just chose this point as point 1 because they gave it to us first, really. So x subscript 1 and y subscript 1. And then this was the second point they gave us, so I said x2 and y2 in that case. Now our slope, we know, is equal to y2 minus y1 over x2 minus x1. So really it's just a matter of plugging in the values that we've basically been given in the problem. y2 is 12. Y1 is 0. X2 is 12. X1 is 9. And so by plugging those in, we end up with 12 over 3. And 12 divided by 3 gives us a slope of 4. So that's really all that they're asking us on this first problem, on these first set of problems. Problem 10, we have a y-intercept of -3 and a slope of -7. We want to know what is the equation. For this, remember that we use the equation or the formula y equals mx plus b, where m is the slope and b is the y-intercept. So what would the equation be? y equals minus 7x minus 3. Yeah, just whatever the slope is, we fill it in here, and then whatever the intercept is, we just fill it in here. I knew what you meant, Kaylee. That's okay. On the test, though, be specific. But yeah, I mean, it's just a matter of putting these numbers into the right place, and we have our answer. And then problems 27 through 32. We worked problems similar to these earlier, where we're given the equation and we want to find the graph and also to label its intercepts. And so we found out how to find the intercepts by plugging in x equals 0 to get the y-intercept and y equals 0 to get the x-intercept. And then plotting those gives us the graph. Okay. That puts us about halfway through section 2. I think we'll go ahead and stop there. That way on Wednesday we can finish section 2 and then continue on into section 4 and finish that as well on Wednesday. And just get through all 3 sections of chapter 2 that we need to cover today. Or this week, not today. So I'm going to leave it at that. I'm going to get an assignment ready for this section and send it to Mrs. Knisley to add it to your My Math Lab or My Lab. And it'll be an assignment for this class, but it's going to be on her section. So I want you to go ahead and work that, and I'll probably have set a due date of Monday next week. I'll give you one for both today and for Wednesday. And rather than going back and do old assignments for like stuff we covered weeks ago, I'll just give you new assignments for stuff that we're covering now, and as we continue to go from here. Okay. And so that'll be set up as a My Lab assignment, and hopefully that'll work out. Okay. So again, you'll access it through your 1324 course, not this course on Canvas. But you should get it once it's assigned. You should get an announcement that you have the assignment and that it does have a due date. And so that'll be for this course. Keep that in mind. Do you have any questions? All right. So we will stop there for today, and I will talk to all of you next time. Y'all have a good rest of the day, and take care. And I'll see you Wednesday.